Welcome back to Revise and Resubmit, and welcome to another weekend book review. I'm Pavlov.
And I'm Nikita. Today, we're plunging into the really fascinating world of vectors and tensors.
Ah, the big one.
Yeah, these mathematical powerhouses. They're behind, well, almost everything, from deep physics to the tech you're using right now.
Absolutely, and we've got some great material to draw on, including Robyn Arianrhod's book, Vector.
Right, which really brings out the human story behind these concepts, doesn't it?
It does, and what's so captivating, I think, is that these aren't just dusty formulas in a textbook.
No, not at all.
Vectors and tensors, they're like fundamental languages, languages we use to describe how the universe actually works.
And how we handle data now, too, increasingly.
Precisely. Think of tensors like Arianrhod probably puts it as a kind of advanced multi-dimensional version of vectors.
Going beyond just direction and magnitude.
Exactly. They let us handle, the fabric of space-time itself, information flow, so much stuff, really elegantly.
Okay, so our mission today, it's not about getting bogged down in equations, right?
No, definitely not the goal.
Instead, we're going on a bit of a historical adventure. We're tracing the, well, frankly, surprising origins of these ideas.
It's a great story, full of brilliant minds, unexpected twists.
Yeah, and this powerful sense of how concepts from centuries ago are just absolutely essential today.
Couldn't agree more. And when you look way back at the earliest mathematical thinking, it's pretty amazing how long the groundwork was being laid.
Okay, let's dig in then. Our sources remind us nearly 4,000 years ago, Mesopotamia. They weren't just, doodling.
Not at all. They had sophisticated multiplication tables on clay tablets.
Wow. That shows a real grasp of numbers, doesn't it? Driven by, practical needs, early economies.
Exactly that. Practical needs. And this sort of early number sense paved the way for something much bigger later on. Algebra.
Algebra, right. And figures like Al-Khwarizmi, the father of algebra.
That's him. A pivotal figure. But it's easy to forget how long that journey was.
Yeah.
For algebra to become symbolic like we know it.
You mean with X's and Y's and stuff?
Yeah. I mean, Harriot's work, 1631, that's when it starts looking properly modern and symbolic. Before that, it was mostly words, descriptions, numerals.
Try solving complex equations like that.
Right. It puts things in perspective.
And even before the symbols really took hold, they had other ways, geometric ways, like alms in Egypt, approximating pi.
Yeah, using an octagon way back around 1650 BCE. Clever stuff. So for literally millennia, people have been grappling with these core mathematical ideas just expressed differently.
Okay, so the thinking was there for a long, long time.
That's right. But the real sort of acceleration towards vectors and tensors, that really kicks off with the calculus revolution, 17th century.
Ah, calculus. Leibniz, Newton.
Independently, yeah.
So what's the crucial bit from calculus for our story?
Well, calculus just gave us a completely new way to think about change. Motion. Dealing with infinitesimally small quantities.
Right.
And Newton, famously, during the plague years, working in isolation.
Incredible.
He used it to formulate his laws of motion, gravity, and his idea of force, proportional to the alteration of motion, acting in a direction. That's a very early, very fundamental hint of vectors, isn't it?
Directionality. Okay. And Newton, he was the secretive one, right? Compared to Leibniz.
Yeah, quite different characters. Leibniz was all about clear notation, making it usable. Newton kept things closer to his chest, you could say. Our source highlights that contrast.
And then, of course, Descartes. Can't forget Descartes.
Absolutely not. The Cartesian coordinate system, that XYZ grid.
Analytic geometry, finally linking algebra and geometry with coordinates.
Exactly. Gave us that framework. It's so fundamental now. You barely think about it.
Yeah.
But even with calculus and coordinates, the specific idea of a vector as its own thing, with its own algebra, that was still coming.
Okay, so foundations are laid. Algebra, geometry, calculus. What's the next big leap?
Well, the emergence of vectors is actually really tied up with the struggle to understand, negative numbers, and especially complex numbers.
Ah, complex numbers. The square root of -1. Always felt a bit weird, abstract.
They did. I mean, even Euler, his amazing formula, EE, Yokus EC, connects exponentials and trig functions.
Super useful, right. Pops up everywhere. Circuits, quantum mechanics.
Incredibly useful. But even Euler was apparently a bit puzzled about what they really were, fundamentally. He didn't have a good geometric picture for them.
So, powerful tools, but still mysterious. Enter Hamilton.
Yes. William Rowan Hamilton. He was obsessed, really, with extending complex numbers from 2D to 3D.
Makes sense, right? We live in 3D.
You'd think. He'd worked with complex numbers as sort of couples of real numbers. De Morgan had hinted they could be understood algebraically. But Hamilton's big moment, Arianrhod calls it seemingly absurd, was realizing that to make multiplication work consistently, not in 3D, but actually in 4 dimensions, he had to break a fundamental rule.
Which rule is that?
Commutativity. The idea that A times B always equals B times A.
Whoa. Okay, that is radical. So multiplication orders suddenly mattered.
Exactly. That led him to quaternions, 4-dimensional numbers.
4 dimensions. So what are they made of?
A scalar part, just a regular number, and a 3-dimensional vector part. And crucially, he figured out the algebra for multiplying these vector parts.
Like the cross product.
Precisely. The cross product, with its right-hand rule, it's non-commutative. Swap the order, P at Q, and you get the opposite direction, minus Q AP.
And developing that symbolic algebra was key. More powerful than just geometry.
Hugely important. It allowed for generalization in ways pure geometry couldn't easily handle.
So breaking that basic rule, commutativity, actually opened up whole new mathematical worlds.
Absolutely. Arianrhod really emphasizes this. Non-commutative algebra, it turns out, is deep. It underpins quantum mechanics.
How?
Well, think about Heisenberg's uncertainty principle. The order you measure things, like position and momentum, actually changes the outcome. That's non-commuting operators at work.
Wow, okay.
And it even shows up in the maths of general relativity. And soon after Hamilton, another mathematician, Cayley, saw the power of this and developed matrices.
Ah, matrices, another non-commutative system.
Exactly. We use them constantly. Solving equations, computer graphics.
Right, transforming things on screen.
And the order matters there too, doesn't it? Rotate, then move is different from move, then rotate.
Yeah, totally. Matrix multiplication captures that.
It does.
It's still kind of mind-boggling how these abstract maths things have such concrete uses.
And it just keeps going. Think about search engines. Google's PageRank.
Yeah.
Heavily reliant on vectors and matrices.
Yeah.
Analyzing all those web links. The core idea is that a site's importance depends on the importance of sites linking to it. Vectors and matrices crunch those relationships.
So when I search that ranking order, that's vectors and matrices working behind the scenes.
In large part, yes. And machine learning, same deal. Huge amounts of data stored and manipulated using vectors and matrices for things like finding related items or understanding queries.
Wild. What about more physical applications?
Robotics is a great one. Programming robot movements, rotations. That's all matrix multiplication, controlling those joints precisely.
Makes sense.
And computer graphics, obviously. Creating the visuals in games, movies, rotating, scaling, projecting 3D onto your 2D screen. All matrices.
So they're really woven into our tech fabric.
Absolutely. From search results to robot arms.
Okay, now the source also brings in the quantum revolution. How does this all connect to the subatomic world? Non-commutative algebra again.
Yes, it comes back in a big way. The quantum world is just weird from our classical view.
Yeah.
You have the Stern-Gerlach experiment showing angular momentum is quantized, comes in discrete packets.
Not just any value is allowed.
Right. Then you get electron spin, this intrinsic angular momentum. And Dirac's relativistic quantum theory demanded specific values for spin.
And Hamilton's quaternions connect to this somehow. That seems unlikely.
It's fascinating. The mathematics of quantum spin is deeply tied to quaternion rotations. It turns out that for particles like electrons, fermions, you have to rotate them 720 degrees.
2 full circles.
2 full 360 rotations, to get them back to their original quantum state. It's completely counterintuitive.
That is, mind-bending.
But that bizarre behavior is mirrored perfectly in the math of quaternion rotations. It's like the universe speaks quaternion at some level.
Okay. Deep stuff. So while Hamilton was pushing quaternions, there was someone else working independently. Grassmann.
Hermann Grassmann,
Yeah.
Developed his own system, the Ausdehnungslehre, linear theory of extensions.
And our source says his book didn't exactly fly off the shelves. Even Gauss wasn't impressed.
That's right. Apparently Gauss gave it a rather dismissive response. Grassmann was self-taught, his style was dense, hard to penetrate.
So what was his system about?
It was more abstract than Hamilton's focus on 3D geometry. More about general linear structures, extensions into higher dimensions. But buried in there were the seeds of tensor algebra.
Interesting. So you had these 2 different streams, Hamilton's geometric quaternions, Grassmann's more abstract extensions, both pushing algebra forward.
Exactly. Different approaches, different notation, and inevitably that led to, well, disagreements.
Yeah.
Debates.
A war, the source calls it.
A bit of an intellectual war, yeah. Hamilton pushed quaternions hard. Tate was a huge supporter. But others, like Airy, just flat out rejected them. Was this the right language for physics or not?
And Maxwell's work sort of settled it. Electromagnetism.
It was a huge catalyst. Maxwell used vector ideas and notation in his revolutionary equations, unifying electricity and magnetism. Seeing vectors used so successfully, that gave them huge momentum.
Made them practical, indispensable tools for physicists.
Right. And then Gibbs in the US and Heaviside in the UK independently took Maxwell's work, took the useful bits from quaternions, streamlined it all, and basically created modern vector analysis.
The stuff we use today, dot products, cross products.
Exactly that. They simplified things, focused on the 3D vector part, developed the notation we still use. So vector analysis kind of won out over pure quaternions for most physics applications.
Okay, so vector analysis becomes the standard. But where do tensors really come into their own? The source mentions invariance. What's that about?
Invariance is a massive idea in math and physics. It means finding quantities or properties that don't change, even when you change how you look at them, like changing your coordinate system.
Give me an example.
Okay, the dot product of two vectors. If it's 0, they're perpendicular. That fact, their perpendicularity stays true no matter how you rotate your viewpoint, your axis. The description might change, the components change, but the underlying geometric fact is invariant.
Right. The relationship itself doesn't change.
Exactly. And that idea is powerful far beyond geometry.
How so? Modern tech.
Think about AI, neural networks. When you're analyzing an image, you want the network to recognize, say, a cat, regardless of whether the cat is slightly rotated or bigger or smaller in the picture.
It needs to identify the catness, which is invariant under those changes.
Precisely. Key features need to be invariant under certain transformations. And look at DeepMind's AlphaFold, predicting protein structures.
Huge breakthrough.
Huge.
Yeah.
And it relies heavily on neural networks identifying these kinds of invariant patterns in incredibly complex biological data as the same core mathematical principle at work.
Amazing how that thread connects. Okay, inevitably Einstein. Relativity.
Yep.
Tensors become crucial there.
Absolutely essential. Now, people like Poincaré and Lorentz were already working on relativity ideas. Lorentz even used some whole vector notation.
Okay.
But Einstein, in his special relativity, initially worked mostly with components. It was actually Minkowski who came along and unified space and time into space-time, introducing the Minkowski metric.
Yeah.
That really gave special relativity a more geometric, tensorial feel.
But for general relativity, Einstein needed something more, didn't he?
Oh, yeah. General relativity is about gravity as the curvature of space-time itself. Describing that curvature, making sure the laws of physics look the same for all observers. That required a whole new mathematical toolkit.
And that toolkit was tensors.
That toolkit was tensors. He needed help, though. He collaborated with his friend Marcel Grossmann, a mathematician.
And Grossmann knew about Riemann's work.
Exactly. Bernhard Riemann had done groundbreaking work decades earlier on the geometry of curved spaces in higher dimensions. He developed the concept of the metric tensor.
The metric tensor, what does that do?
It's basically the tool you use to measure distances and angles within a curved space. Gauss had even touched on similar ideas, studying the curved surface of the Earth for surveying.
Right, measuring on a sphere isn't like measuring on a flat map.
Precisely. And Riemann developed the mathematics for this in general. The Riemann tensor specifically is the object that mathematically captures the curvature of a space. It became central to general relativity.
So Riemann's abstract math found its killer app in Einstein's theory of gravity.
You could say that, but the actual calculus of tensors, the rules for manipulating them, that was largely developed by Gregorio Ricci and his student Tullio Levi-Civita in Italy.
Ricci, didn't he have a tough time getting recognition?
He did, apparently. But he developed what he called absolute differential calculus, what we now just call tensor calculus. It defined how tensor components transform when you change coordinates.
Those indices you see on tensors, like t subscript to mu nu.
Exactly. Those indices tell you precisely how the components must change to keep the underlying physical or geometric quantity invariant. It's intricate, but incredibly powerful.
You see tensors in other fields too, right? Like materials science?
Oh, definitely. The stress tensor, for example. It needs two indices because it relates direction of force to the orientation of the surface it acts on. Complex relationships.
Or even language processing now. Tensor product.
Yeah, capturing relationships between words by combining their vector representations in multidimensional ways. Tensors are spreading everywhere.
So, back to relativity. The metric tensor is the key invariant thing.
Well, the interval it defines is invariant. In general relativity, the metric tensor, again, defines the space-time interval, ds-saw. It's like the Pythagorean theorem, but for curved 4D space-time. And crucially, unlike in flat space, this metric tensor again isn't constant. Its components change depending on where you are in space-time, reflecting the curvature caused by mass and energy.
So it measures distance in this warped, gravity-affected geometry.
That's the idea. It encodes the geometry itself.
Which brings us finally to Einstein's field equations. The heart of it all. Tensor calculus made those possible.
Absolutely. You need tools like covariant differentiation, a way to take derivatives correctly in curved spaces using things called Christoffel symbols. Einstein, with Grossman's crucial help with the math, used all this tensor machinery to link the geometry of space-time directly to its content.
Geometry on one side, mass and energy on the other.
That's it. The field equations basically say the curvature of space-time, represented by the Ricci tensor, derived from the Riemann tensor, is proportional to the distribution of mass and energy, represented by the stress energy tensor.
Rune related to teen. Utterly profound.
Profound and mathematically beautiful. It took enormous effort, and Hilbert was working on similar ideas independently around the same time, too.
And the story doesn't quite end there. Emmy Noether.
Emmy Noether. Phenomenal mathematician. Her theorems established this incredibly deep connection. Symmetries in physical laws correspond directly to conservation laws.
Like conservation of energy.
Exactly. Her work has huge implications for general relativity, particularly around the conservation of energy and momentum in curved spacetime, which is actually quite subtle. Levi Shivita also did important work connecting tensor calculus to energy momentum conservation in GR.
It all ties together.
It really does. You see how indispensable all these things became? Algebra, calculus, imaginary numbers, vectors, quaternions, matrices, tensors, they all built on each other.
From ancient counting to Einstein's equations and, well, the phone in your pocket, it's an incredible journey.
It really is. What strikes me is just how unexpected it all was. The twists, the debates, the sheer flashes of brilliance, and how these abstract ideas ended up being so unbelievably practical and fundamental.
Yeah. So, as we wrap up this deep dive, maybe something to think about. These mathematical languages, vectors, tensors, they're still evolving, aren't they?
Constantly.
And they keep shaping how we see reality, how we build technology, often in ways we're only just starting to grasp.
Makes you wonder what's next, doesn't it? What new insights, what new tech will these tools unlock down the road?
Absolutely. A lot to ponder there.
And don't forget to subscribe to Revise and Resubmit on Spotify and Apple Podcasts. Until next time, keep those minds curious, keep questioning, and keep revising and resubmitting.
রিভাইজ অ্যান্ড রিসাবমিটে স্বাগত। আপনারা শুনছেন আমাদের উইকেন্ড বুক রিভিউ পর্ব। আমি নিকিতা
আর আমি পাভলভ। আচ্ছা, তাহলে আসুন আজকের সূত্রগুলো নিয়ে একটু গভীরে যাই। হাতে আছে রবিন এরিয়ারহডের ভেক্টর বইয়ের কিছু অংশ আর নোটস। আজ আমরা দেখব কিভাবে ভেক্টর আর টেন্সরের মতো গাণিতিক ধারণাগুলো আধুনিক বিজ্ঞান আর প্রযুক্তির পথটা তৈরি করলো। আমাদের আজকের কাজটা হলো এই বিশাল ইতিহাস থেকে জরুরি আর চমকপ্রদ বিষয়গুলো বের করে আনা।
হ্যাঁ, আর বিষয়টা কিন্তু শুধু ফিজিক্সেই আটকে নেই। জেনেটিক্স বলুন, সার্চ ইঞ্জিন, এমনকি আর্টিফিশিয়াল ইন্টেলিজেন্স, এই সব ডেটা নির্ভর জায়গাতেও এই ধারণাগুলো কিন্তু একদম মৌলিক। আজকের এই আলোচনায় আমরা একটু বোঝার চেষ্টা করব কেন এই গাণিতিক চিন্তাগুলো এত প্রভাবশালী হয়ে উঠল আর কিভাবে তারা আমাদের পৃথিবীকে দেখার ভঙ্গিটাই বদলে দিল।
শুরু করা যাক ভেক্টর দিয়ে, যার মান আর দিক দুটোই আছে। শুনতে তো বেশ সহজ মনে হয়, কিন্তু এর পেছনের গল্পটা বেশ লম্বা। উইলিয়াম রোয়ান হ্যামিল্টন যখন এই 3D রোটেশন বা ত্রিমাত্রিক ঘূর্ণন বোঝানোর একটা ভালো গাণিতিক উপায় খুঁজছিলেন, যা সাধারণ বা কমপ্লেক্স সংখ্যা দিয়ে ঠিক হচ্ছিল না,
ঠিক তখনই তো তিনি কোয়াটার্নিয়ন আবিষ্কার করেন।
হ্যাঁ, ওই চারমাত্রিক সংখ্যা যাতে স্কেলার আর ভেক্টর দুটোই ছিল। কিন্তু সবচেয়ে অবাক করা বিষয় ছিল ওনার ওই আবিষ্কারটা যে কোয়াটার্নিয়ান গুণন বিনিময় নিয়ম মানে না। এ গুণ বি আর বি গুণ এ সবসময় এক হবে না।
একদম। আর গণিতের এই খুব সাধারণ নিয়মটা ভাঙা, এটাই ছিল আসলে একটা যুগান্তকারী ব্যাপার। প্রথম দেখায় অদ্ভুত লাগলেও এই নন কোমেটিভ বা বিনিময় অযোগ্য গুণনই কিন্তু কোয়ান্টাম মেকানিক্সের মতো ভবিষ্যতের অনেক কিছুর ভিত্তি তৈরি করে দিয়েছিল।
তার কি এই যে খুব ক্ষুদ্র স্কেলে বাস্তব জগতে আমরা কোনো ক্রমে জিনিসগুলো মাপছি বা দেখছি, সেটাই ফলাফলের অংশ হয়ে দাঁড়ায়।
এটা তো আমাদের প্রতিদিনকার অভিজ্ঞতা থেকে বেশ আলাদা।
ঠিক তাই। হাইজেনবার্গের যে অনিশ্চয়তা নীতি, তার মূল কথাই তো এটা মানে একটা কণার অবস্থান আর ভরবেগ একই সাথে একদম নিখুঁতভাবে মাপা সম্ভব না, আর কোনটার পর কোনটা মাপা হচ্ছে সেটাও ফলাফলের উপর প্রভাব ফেলে।
হ্যামিল্টনের কাজটা শুধু 3D ঘূর্ণন বোঝাতেই সাহায্য করেনি, বরং বলতে গেলে পুরো অ্যালজেব্রার জগৎটাকেই অনেকটা প্রসারিত করেছিল, নতুন সম্ভাবনার দরজা খুলে দিয়েছিল।
আর প্রায় একই সময়ে তো জার্মান গণিতবিদ হারমান গ্রাসমানের কাজও চলছিল, যদিও সেটা ছিল আরও বেশি বিমূর্ত, তাই না?
হ্যাঁ, ওনার কাজ থেকেই ধীরে ধীরে টেন্সর অ্যালজেব্রার ধারণাটা জন্ম নেয়। যদিও হ্যামিল্টন বা গ্রাসম্যান কাউকেই তাদের সময়ের বিজ্ঞানীরা সহজে গ্রহণ করেননি। তাদের ধারণাগুলো ছিল বড্ড অচেনা।
স্বীকৃতি পেতে অনেক সময় লেগেছিল তাহলে।
হ্যাঁ, লেগেছিল। কিন্তু পরে জেমস ক্লার্ক ম্যাক্সওয়েলের হাতে এই ভেক্টর একটা দারুণ শক্তিশালী হাতিয়ার হয়ে উঠল, যা ক্ষেত্র বা ফিল্ডের মাধ্যমে কাজ করে। এটা কিন্তু তখনকার ওই দূর থেকে ক্রিয়াশীল বল বা অ্যাকশন অ্যাট এ ডিস্টেন্স ধারণা থেকে সরে এসে ফিজিক্সকে একটা নতুন ভাষা দিয়েছিল।
ম্যাক্সওয়েল যেমন ফিল্ড থিওরি দিয়ে দূরত্বের ধারণাকে বদলে দিলেন, তেমনি অ্যালবার্ট আইনস্টাইন যখন স্থানকাল নিয়ে ভাবছিলেন, তার আরও গভীর এক গাণিতিক কাঠামো দরকার পড়ল। এখানেই তো টেন্সরের গুরুত্বটা সামনে আসে, তাই না?
ঠিক ধরেছেন। সাধারণ আপেক্ষিকতা তত্ত্বের জন্য আইনস্টাইনের এমন একটা গণিত দরকার ছিল যা স্থানকালের জ্যামিতি, তার বক্রতা আর কিভাবে মাধ্যাকর্ষণ কাজ করে সেটা ব্যাখ্যা করতে পারে। টেন্সর ঠিক এই কাজটাই করতে পারত।
এই টেন্সরের মূল শক্তিটা আসলে কোথায়? প্রায় যে শোনা যায় ইনভ্যারিয়েন্স বা অপরিবর্তনীয়তার কথা, বিষয়টা ঠিক কি?
অপরিবর্তনীয়তা বা ইনভ্যারিয়েন্স মানে সহজ কথায় বললে নিয়মটা একই থাকা। আপনার দেখার ভঙ্গি বদলালেও, ধরুন ঢাকার রাস্তায় একরকম ট্রাফিক নিয়ম, নিউ ইয়র্কে হয়তো আরেক রকম, কিন্তু নিয়ম মেনে গাড়ি চালানোর যে মূল ধারণাটা সেটা তো একই থাকছে শহর বদলালেও।
আচ্ছা,
ফিজিক্সের সূত্রগুলোও তেমনই। পর্যবেক্ষক বা কোঅর্ডিনেট সিস্টেম বদলালেও মূল সূত্রগুলো বদলায় না। টেন্সর হলো এই অপরিবর্তনীয় মূল সত্য বা নিয়মটাকে ম্যাথমেটিক্যালি লেখার একটা অসাধারণ উপায়।
তার মানে এই একই গাণিতিক কৌশল যেটা মহাবিশ্বের নিয়ম বুঝতে আইনস্টাইন ব্যবহার করেছিলেন, সেটাই এখন গুগল সার্চে ওয়েবসাইটের র্যাঙ্কিং ঠিক করতে, বা ধরুন ডিপ মাইন্ডের আলফাফোল্ড প্রোগ্রামে প্রোটিনের জটিল 3D গঠন বুঝতে কাজে লাগছে। এটা তো দারুণ একটা সংযোগ।
হ্যাঁ, কারণ টেন্সর বহুমাত্রিক সম্পর্ক আর প্যাটার্ন ধরতে পারে, যা সাধারণ ভেক্টর বা স্কেলার দিয়ে সবসময় সম্ভব না। যেমন ধরুন আলফাফোল্ড প্রোটিনের গঠন বুঝতে টেন্সর ব্যবহার করে, কারণ অ্যামিনো অ্যাসিডের মধ্যে যে জটিল 3D সম্পর্কগুলো আছে, কে কার পাশে কিভাবে ভাঁজ খাচ্ছে, এগুলো তো পর্যবেক্ষকের দেখার অ্যাঙ্গেল বদলালেও একই থাকে। টেন্সর এই অপরিবর্তনীয় মূল কাঠামোটাকেই ধরতে পারে। সার্চ ইঞ্জিনের র্যাঙ্কিংয়েও অনেকটা এভাবেই বিভিন্ন ওয়েবসাইটের মধ্যেকার সম্পর্ক বিশ্লেষণ করা হয়।
তাহলে এই পুরো যাত্রার সারমর্মটা কি দাঁড়ালো? ভেক্টর আর টেন্সর মানে হ্যামিল্টন গ্রাসম্যানের বিমূর্ত চিন্তা থেকে শুরু করে ম্যাক্সওয়েল আইনস্টাইনের যুগান্তকারী তত্ত্ব, আর সেখান থেকে আজকের এআই পর্যন্ত, এই ইতিহাসটা আসলে আমাদের দেখাচ্ছে যে গণিতের গভীর ধারণাগুলো কিভাবে ধীরে ধীরে বাস্তব পৃথিবীর প্রযুক্তি আর জ্ঞানকে এগিয়ে নিয়ে যায়।
এখানে একটা বিষয় কিন্তু ভাবার মতো। হ্যামিল্টন বা গ্রাসম্যানের ধারণাগুলো তাদের সময়ে গৃহীত হতে এত বাধার মুখে পড়েছিল কারণ সেগুলো ছিল খুব অচেনা, একদম প্রচলিত চিন্তার বাইরে। কে বলতে পারে, হয়তো আজও আমাদের সামনে এমন কোনো বৈপ্লবিক গাণিতিক বা বৈজ্ঞানিক ধারণা ঘুরছে যা ভবিষ্যতের চাবিকাঠি হতে পারে, কিন্তু আমরা এর গুরুত্বটা এখনই ঠিক বুঝতে পারছি না। এই সূত্রগুলো আসলে সেই দীর্ঘ, কঠিন কিন্তু শেষ পর্যন্ত সফল যাত্রার কথাই মনে করিয়ে দেয়।